Righto, good evening and welcome. Hey everybody, sorry I'm a little late or something. There we go. Yep, just thought I'd get on anyway, see if I could get through as much of this next section that we were working on. There, yeah, that one. All right, we are looking at the Chapter 2 review questions for Calculus 2. So we were chatting last time with somebody who wanted to see some differential equations, and see if we can get through a bit of our unit review before we have to get to bed and all that. So, actually, you know what? Let me pull this a little bit wider. Looks pretty good. Righto. So thanks everybody for coming. Hope you're having a good Wednesday. I did a double session of Tai Chi today, and whoa. First session we worked on the form. There was another student there, so we had good amount of split time between the two of us. Did warm-ups, did work on the form for pretty much the whole rest of it. And then we did some what was the other bit? Oh, it was just like stretching and stuff. So, we did a guided meditation. That was fun. Right. So that will not stand. Okay. All right, so for Calculus 2, question number 1. Consider the following sequence x sub k, given by the formula. X sub k is equal to cosine of k pi times the sine squared of k all over the eth root of k. K is going to be every integer greater than or equal to 1. So this is going to be z positive. If this sequence converges, what is its limit? And it gives me 5 answers, which are all numbers. I mean, kind of spoilers there. All right. A is 0. B is 1. C is natural log of 2. D is eth root of 2. And E is eth root of E. All right, so for this formula, we have a particular, we have a particular formula listed here, and then we want to find out what's going to happen if we take the limit as k goes to infinity. So if the sequence converges, okay, so this is not even the sum either. This is just the sequence. So we want the limit as k goes to infinity of x sub k. So for this particular limit, we want to look at all of the individual terms that are in here. We don't actually have to worry about series convergence, at least yet. However, just out of curiosity, right? What is the beginning of this particular chapter? So, when we go back, right? Cool. So yeah, this is before L'Hopital's rule ever shows up. So good news, we don't have to do that. Also good news, we don't have to do like the ratio function or anything. Sorry, ratio test or anything like that. So we should be able to just say what's the limit as k goes to infinity of cosine k pi times sine squared k all over eth root of k. So, in terms of rules, we do have that the limit of a product. So what we have here is three terms which are being multiplied together. Yes, okay, there's something that's being divided, but realistically it doesn't really matter. Multiplied, divided, it's all the same stuff. The limit of the product is going to be the same as the product of the limits. So we can, in fact, say that this is going to be the limit as k goes to infinity of cosine of k pi times the limit as k goes to infinity of sine squared of k over the limit as k goes to infinity of eth root of k. Okay, now the top two bits. Are oscillatory. So the cosine of k pi will always be between -1 and +1. And the sine squared of k is always going to be between 0 and 1. That's it. And the limit as k goes to infinity of this bit. Boy, this is why I don't stream this late. Right, this is going to go to infinity. Which means what we have is a bunch of stuff up top, which is somewhere between -1 and +1, depending on the individual values of those products. But they will never be more than 1 because both, right, at least one of those numbers will be, I guess I can't necessarily say that 100%, but at least one of those numbers will be smaller than 1 magnitude-wise, and so it's going to make the other one smaller than it is currently for whatever value we've got. Right, no matter what value either of them are, 1 is always going to be smaller than 1 magnitude-wise. So for the cosine of k pi, all of the values of 1 and -1 are going to be when those are whole pies. Right? So whenever k is an integer, what do you know? Those are the numbers we get. Right? Because it's just going to be 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, etc. So realistically, this is going to be the same as -1 raised to the, is it just k? Yes. Right? It's going to be equivalent to -1 raised to the k. In this particular case, right? Just happens to work out that way. Whereas the sine value is never going to end up being on a nice multiple of pi because k is always just going to be a whole integer. So we're just going to get values that are never a nice multiple of pi, never a nice multiple of pi over 2 for that matter. Oh, you're right. Pi over 2 would get us our 1 value. So this is always smaller than 1 every single time. And again, this one is just equivalent to the oscillation -1 raised to the k. So then we look at this, and this is, okay, so this is going to be -1 raised to the k times this sine squared thing, which is going to end up being, still need the limit. As k goes to infinity, our sine squared of k is again just between 0 and 1. And then the bottom stuff is going to infinity. This is poor form, but nonetheless. Right? This is either -1 or +1, and this is small. Doesn't matter what it is. It's smaller than a value of 1. The denominator is going to infinity, so that's a huge number in the denominator of this particular limit, which is going to make the limit as k goes to infinity of x sub k equal to 0. And that's our A. So just think about the future values that we're going to get out of these things. What could we possibly get out of a cosine function, right? Cosine of k pi. Again, that's going to get us stuff that's between -1 and 1. Which stuff? Well, since k pi is always going to be a nice multiple of pi, our cosines are either going to be a -1 or a +1. And that's it. And then our sine squared function, with us hitting whole values of whole k's, right? So it's just going to be 1, 2, 3, 4, 5. We're never going to get any of those nice values for a sine function. And this especially, considering k has to be greater than or equal to 1 in the first place. It could have been 0 at k equals 0, but there is no k equals 0 for this. We were assuming that our k was going to be part of the positive integers, not 0. Right. If anybody does have any questions about anything in particular, whether that is something related to this or completely not related to this, feel free and ask. I will derail myself for 2 hours of a conversation that is about something completely different. That is perfectly fine. This really, like the cracking the GRE stuff, is, nice for the people who actually want it on YouTube. But for the most part, it serves as a framework to be able to talk about different kinds of problems. Okay. This also means we should probably change the title of that other one we had a couple of weeks ago, or last week. Yeah, Night 32, lol. Spent like 5 minutes on it. It's fine. All right. Number 2. Let x sub n be the sequence x sub k, because this is how we do it here. Sequence with x sub 1 is equal to 2, and x sub k is equal to square root 5 x sub k minus 1 plus 6 for all k belonging to positive integers except not 1. Go figure. Well, okay. Because we're defining x1 here, then we do need to technically exclude it down here. Could just come up with x0, I mean, honestly. Okay, given that this sequence converges, what is the limit? All right. So given convergence, what is the limit? Here we want to say, all right, we're starting with a value of 2 in there. Um, right, so this is probably not exactly helping at this exact moment in time. So we need to approach this a little bit different. Right, this also change. All right. Not quite that easy. One of the things we could do is find out what the limit is of the ratio. Right, so if we take the ratio of the current value compared to the previous value, then that's going to tell us a trend. And specifically, as k goes to infinity, is that trend going to be like a continuous multiplier? So are we going to get a particular number, like 2, for example? 2 would be the constant multiplier of y equals 2 to the x, or any of its family of functions. So here we want to go with the same sort of thing. We want to know if there is a connection between x sub k and x sub k minus 1. And if there is, what that is going to be. Make sure nothing's pulling. Okay. Right on. So one of the ways we could set this up is as a limit as k goes to infinity of the thing we just had, the square root of 5 x sub k minus 1 plus 6 all over x sub k minus 1. Sorry, that's the eth root, I think. Oh no, is this just square root? This is just a square root, this one. Okay, so one of the things we can do here is we say that it's just telling whether, yeah. That's just saying whether it's going to converge or not. So this is not going to work out terribly well. Right, so I realized what's going to happen here. We're going to say that this is going to be the limit as k goes to infinity of the square root of, and then what we're going to get is 5x sub k minus 1 plus 6, all divided by x sub k minus 1 squared on the inside of this square root. And then both of those are going to have now x sub k minus 1s in the denominator, which is then going to say that the limit of this thing is 0. So that is actually as expected. Right, given convergence. Okay, so let's try and get an explicit form of this sequence. So currently it's implicit, which means it's based off of all the any of the previous values. So here we have x sub k and x sub k minus 1. So instead of that, what we want is to make sure that our function is going to be based solely on the value of k that is present. It is not going to have anything to do with x sub k minus 1. Okay, so let's just run through what we've got so far. Values for k and values for the square root of 5 x sub k minus 1 plus 6. Okay, so we are given. Actually, that's right. Not that. It's x sub k. So 1 matches with 2. 2, we're going to take that 2, we're going to plug it in. So that now becomes the square root of 5 times 2 is 10, plus 6 is 16, which gets us 4. Right? 3 is that we take the previous value, 4, we plug it in, we get 20, plus 6 is 26, the square root of 26. This is the square root of 16, and this is just 2. Right, 4. This is going to be, I see the problem. Big square root. 5 root 26 plus 6. Yeah, that does cause a bit of a problem. Because the next is going to be the square root of 5 times that thing plus 6. So it's just getting uglier and uglier as we go. Alternatively, I do believe that can be... This is more of a pre-calc thing. the square root of 5 root 26 plus 6 is equal to, we'll just call it x for the moment. That's not a good idea. Is going to be s for square root. Sure, why not? All right, so that means that 5 square roots of 26 plus 6 are going to be s squared. That might be a mistake. Hang on. How do we do it in the other case? So there is a simple case like this that shows up in sums and differences all the time. I think there's a way to do it by multiplying by square root of 1 minus root 2. Messes with stuff a little bit. Right. This is much nicer, although it does give us a imaginary number. So that does not technically work for what I was doing. Yeah, it was the other way around too. So doing this multiplying by the multiplying by the irrational conjugate should then allow us to end up with, this is 2 and this is a minus 1. So this is just going to be the square root of 1, which is just 1. Okay, so here we could actually do the same thing. Don't do the s squared thing. What we're going to do is we're going to multiply both sides of this equation by irrational conjugate. Square root 5 root 26 minus 6. This is going to be this is going to be 25 times 26 minus 36, which is, again, just a number. So it does help out a little bit. Now the problem is that it's also that same conjugate over in the other side. So how do we resolve this? I think we actually had the other form of it, so it still worked. So we had two different forms, we just proved that they're the same. So what I want really is an alternate form of that, which does not involve a nested square root. I'm like almost positive that the way to do it ends up being something with rational conjugates, irrational conjugates, and it can't be this because that just shifts it to the other side. That's 650. 650 minus 36 is 614. Hmm. Okay. So I guess if we were doing an actual test on this, one of the ways to do this is to grab your calculator and then get it put into your calculator so that you can just do this numerically. So on a TI, for example, I would say like plug in 2 gets stored to your X value. So your TI language is going to be 2 store to X. Then you type in square root 5x plus 6 store to X. And then just repeat this instruction as many times as is necessary until you get it. So generally speaking, these sorts of things are going to clean themselves up fairly quickly. But one of the things that we could do is kind of look at where this is going in terms of the numbers. So root 26 is just barely greater than 5. 5 square roots of 26 is going to be about 25, just a little bit more. Plus 6 is going to get us 31, a little bit more. And then we're taking the square root, so it is going to be less than 6. Right, so we can make a couple of guesses if we don't have anything particularly, and that is, okay, what is this whole value then on the inside of this? Well, that's going to be 5 root 26 is again just over 25. And then plus 7 is going to get us, right, like I said, just over 31. Square rooted is, 5.3 something. I don't know. Plug that back in. 5.3 times 5 is going to get us 26, 27 plus 6 is going to get us about 33. So it's still going to be increasing probably. And then as we keep thinking about this, right, how is that going to get close to anything in particular? Well, we could take, for instance, what if the value of x got really close to, let's say, 6? Right? If it was 6 times 5, that'd be 30, plus 6 is 36. Take the square root, it's 6. So we could see it cycle around and find itself again and again and again. So you can intuit your way through these questions. It's just not really like recommended. So A was, or the other option, right? Just plug in the numbers that you have here. If it's not a steady state solution, then it's not the limit. Right? B is going to be 6. We already know that this is going to be a steady state solution because if you plug 6 in for x sub k minus 1, your x sub k is going to be 6 again. All right, C, 8, D, 10, and E, 16. I'm not sure why any of them would be good distractors, apart from just picking even numbers. But yeah, plug in 4 in for x sub k minus 1, you end up getting 26. That's one of the ones we already had. Right, and then just keep going again and again and again. It's going to still raise the value. 8 times 5 is 40 plus 6. 46 square rooted is just under 7. So then 7 times 5-ish is going to be 35. Plus 6 is 41. And now notice we're decreasing. Square root of 41 is 6.5. 6.5 times 5 is going to get us 32.5. Plus 6 is 38.5. And now we're getting even closer. So we're approaching 6 from both directions here. All right, 10, also going to do the same thing. That's going to be 56. Take the square root, and we're going to be 7.5, right? And then 7.5 times 5, we run into the same thing. It's like 37.5 plus 6 is going to be 43. 44. Right? So again, 10 and also 16 then are going to start shrinking values until they approach 6. Actually, that's not even true. That's just going to be, right? The floor function of x is going to be equal to x if x is an integer of any kind. Um, or it's going to be k where k is going to be the next integer less than or equal to, I guess we don't even need that other statement. Nearest. Let's not say next, because that might get confusing. Nearest integer less than or equal to x. All right, so those of you who don't know your floor function, we got values that are on all of our whole numbers, then we end up with just literally those numbers. Okay, but if the floor function is asking for what's the value that we're going to get, well, if we pick a value that's in between, we're going to get the nearest integer that is less than or equal to that number. So that's going to hop back to here. That is going to be 4. And then we're going to translate that across to where this one is. It's going to have the exact same value. Until we get right underneath that particular point. In this case, 4.99999 infinite, quote unquote, infinite number of nines, at which point there's going to be an open circle stating that there is no point here. It's just going to jump up to the next one. So, same thing's going to happen with all these others. Okay, so what's the actual question? If n is a positive integer, if k in this case, oi, then limit k goes to negative k in the negative direction of absolute value x minus floor x minus the limit as k goes to k from the negative direction. Wait. Oh, that's the problem. X, right? X goes to... I just read it wrong. It's fine. Goes to k from the negative direction of absolute value x minus floor x. Same thing, I think. Yep. Okay. A is -1, B is 0, C is 2, D is 2k minus 1, and E is 2k. Alright, so this is the limit as x goes to -k from the negative side. Where k is a positive integer of the absolute value of x. Now, we should be able to just break this up and say that our x is going to go to -k from the negative side of absolute value of x, and also subtracting the limit as x goes to -k from the negative side of the floor function of x. Should be able to do that. And then other side as well. Limit x is going to go to k from the negative side of absolute value of x minus, so then that's going to be a plus. X is going to go to k from the negative side of the floor function of x. Okay, so first of all, absolute value of x is an even function. Which means that the absolute value of x is equal to the absolute value of negative x. So with this, we have the limit as x goes to -k from the negative direction of absolute value of x, and limit as x goes to k from the negative direction of absolute value of x. With those two things, right, this is an even function. They're going to be approaching the same value, even though they're not actually the same exact value. So they're both coming in like this, but the thing is that they're not coming in like that, coming from the positive side and coming from the negative side. They're coming from both the negative sides. So this one's going up into whatever our limit value is, and this one's coming down into whatever our limit value is. But their limits are going to be symmetric of each other over x equals 0. Right, if we wanted to be like super picky, we could say that this one's going from this is doing like x minus delta and that's going to L from the negative side plus epsilon, whereas this one is going to be the absolute value of x minus delta, and that's coming from L minus epsilon. So the limit value is going to be the absolute value of negative k or the absolute value of k. They're identical to each other. Right, the limit values are symmetric, which tells us that, again, the only thing that's going to really be different is the teeny amount that we're off by. But since we're going off to like this particular k value, there is going to be a decreasingly small epsilon, which is going to keep decreasing and decreasing and decreasing forever. So we don't have an epsilon really. Both of those things are going to L. And because one of them is positive and one of them is negative, they're going to subtract out. Okay, and then we want the same deal with the others. All right, ad break's about to start here, so we'll come back to this in just 3 minutes. Gonna go, and I recommend everybody cycle water. Go and refill your cups if you need to, empty other aspects if you need to. Grab a snack, stand up, stretch, do some workouts, whatever. So, be right back. Thanks so much for coming. Alright, welcome back. We are going to do our Tai Chi form again. Learned another section of it this morning, so afternoon, whatever it was. I don't know. I woke up and then I went to Tai Chi. So So keep your feet rooted to the ground if you're going to do this as well. And tuck into the inguinal crease, which is that spot right between your abdomen and your thigh. And then push out at the same time as your hand starts falling downward, both front and back. And then it ends up whipping quite nicely. And it helps to warm up your joints as well as all of the like connective tissues and cool stuff like that. All right, then do the same here, just up the front and bounce on your toes every so often. Bend the knees just slightly in order to cause your hands to go up like a swing. Trying to use as little energy as possible to keep the arms up. All right, forward and backward. Keep the feet rooted to the ground and just shift weight. Same deal here. Trying to keep the arms swinging as if they're on a swing set. And without making any real jerky motions, because otherwise you might hurt yourself. I do highly recommend learning some Tai Chi, especially if you are a bit older like me. Ugh. I'm sure somebody teaches it near you. Just make sure that they're kind of reputable and not trying to teach you a bunch of woo, because there's also that. All right. So, the form starts feet in a V shape, up like, right, extend the fingers just a little bit, and then round out the arms, and then we first tuck into the inguinal crease, straighten and move the left foot, move to the middle, and shift the right foot. Then we do our breathing, in 2, out 2. Make the energy ball turn on the heel to the right, shift weight forward. Once we get here, shift left foot forward, ward off, turn the right foot. Once we get here, we turn on the toes of the right foot, and then step out and shift weight as we go with a ward off right, turn the right foot. How far off am I? No, it's not too bad. And from here we do a roll back. So we move the left arm down more or less to the elbow, roll through like this, rejoin our hands together and press. lean forward, break apart, lean back, push, lean forward, keep the arms up, lean back, and then we turn on the right heel to the front in this weird pigeon-toed sort of stance. Comes this way, we lean back to the right hip, kind of tuck out like this, and then as we lift up the left heel, we also are going to do a single whip with the right hand. Left side comes out, and then as we shift our weight, we also turn left hand and left foot. These all come down. Do a lift hands to the front. There's basically no weight on my front foot. It's just heels touching the ground. And then we come back. Everything comes in, and then we do a shoulder strike. From here, we turn everything slightly to the left, tuck into the inguinal crease, come up and do a white crane. I told you this before. My instructor actually went to Malaysia to learn Tai Chi better, and he was like, it's a white crane move, I don't understand it. And then he saw a white crane out the bus window, like doing this in a field, and he's like, huh, all right. All right, so we do a brush parry, brush parry. This comes over to here, this comes over to here, and then they both come through. This as a brush parry and this as a strike. And they both come up together. Left leg goes out, strumming the lute. And that's where we switch to, let's go this way instead. Because now I learn. I've got more room this way. I don't have to keep shifting every time I do a move. Okay, so we do strum the lute, and then here we do another brush parry like this. And then this is the thing that I learned last week. This is where the punch starts. So we turn, lean back, turn 45 with our front foot, and then as the foot comes down and we lean forward, the right hand forms a fist and goes down. Then we do our kick move. This is going to essentially run down the person's, I'm going to put my foot against the person's shin and then just run down and try and essentially break the ankle is the idea. So come down like this. We step through. We do a parry or like a block with the fist this way, and then the parry comes with it. And then we take I need to be 90 degrees with my foot. And then we just step through. And we do I did that wrong. Actually, okay. So we're here. The fist is going to come straight out. The hand is going to come over to this side to like help block anything that might be trying to attack. And then we're also shifting the back foot to 45-degree angle instead of 90. Then, this is what I learned today. From here, we shift this around. We roll the shoulders over. And then what we're going to do is, essentially, we're taking the weight of like somebody pressing up against us with the left hand, and it goes through like this. So now it's on my left hand instead of being on my right like this. So from here, roll through like this, open, pull back. Yep. Now I need to get that way. How did that happen? We go like that. Oh, yes. There we go. Okay, so we step up. We step up and turn. We're doing just like we did with the single whip back there. Pull this through like that. This is coming up to, where are we standing? Standing there like this. Yeah, there we go. Okay. So we're standing there like this. This is at 45. We turn. How do we turn? Oh, yep. We got to do a press, or we got to do a push first. So here we pull this through, and then we press in like that. So now that we push somebody, now we can lean back and then twist over like this. Our feet are at an awkward angle again, and then we go up, around, and right hand in the back rest against each other this way. Lean slightly left and hang the left arm on the right arm. And then that is the first third of the Tai Chi form. Oi. My instructor said I have the first, like, half of the moves down. And it is the first third of the form. So, was working with a lady today who, he said she is 74 years old and still doing pretty well. She was taking this this particular class as a like supplement. So that's wrong. It's better. You got these cheese twists over here. They're about, roughly speaking, that big. They're like all soft bread and stuff. It's very good. Hashtag not sponsored. All right, so to do the rest of these, we have this negative limit x goes to negative k from the negative side floor x plus limit x goes to k from the negative side of floor x. Okay, now if we take our diagram we had up here and then we extend this into the negative region as well, it's going to look like that. Right, so if we take 1 and negative 1 as an example, as x approaches -1 from the negative side, it's going to be down here. So we would get a -2. Whereas if x is approaching k, which again is 1, from the negative side, we end up with a 0. So I think that is always the case. So if we do 3 and -3, right, then we end up from the negative side, we've got 2, and from the negative side on the negative number, that's going to be a -4. Whereas up here, this is at 2. So for k, what is then going to be the negative limit floor x plus limit floor x with x going to k from the negative direction and x going to -k from the negative direction. So we got a, in the case of 1, we got a 0 plus a -2, which the -1 becomes the opposite sign, so it becomes positive. So that's going to be 2 plus 0. So at 1, we got 2. It looks like it's going to be 2n. So then we can test this hypothesis with the next one. At -3, okay, 3. I mean, either way, right? Well, no. Okay, it has to be positive integer. We discussed that. K has to be a positive integer. So at 3, on the negative side, we get a -4, which becomes +4 plus, this one's going to be 2. So yeah, we get 6. So it's going to be 2k. And yes, at least that is what my spouse got, so 20 years ago. All right, 3. No, 4. Evaluate the following limit. Limit as x goes to 0 of, nope, not even close. Arc sine of x minus x all over x cubed. Okay. So first off, verify that this is some sort of not easy, something that requires some other attention, right? So this is going to be, if we were to plug this in just as is, we would get arc sine of 0 minus 0 all over 0 cubed. All right, so for arc sine, we're asking for what angle do we get a sine value of 0? So that's going to be at 0. Since this is an indeterminate form, we're not able to figure out what the limit of 0 over 0 should be. Again, we've discussed this before. It could be that this is going to infinity, so that the top is bigger. It could be going to 0, in which case the bottom is bigger. It totally is. Well, okay, as x goes to 0, this is different. Right, as x goes to 0, if the denominator ends up getting us a small number, there we go, which I'm pretty sure that is the case here, then this whole thing goes to 0. Now, if the denominator goes to a small number faster, which I think is the case in this case, then we should get something that blows up to infinity. There we go. Since it is an indeterminate form, we'll use L'Hopital's rule, which states that the limit is going to be the same for a function divided by another function, or that function's derivative divided by the other function's derivative. So the limit as x goes to a of f of x over g of x is going to be the same as the limit as x goes to a of f prime at x over g prime at x. So this is the limit as x goes to 0 of, right, we take the derivative of an arc sine, and we get 1 over square root 1 minus x squared. Let me double check that in a second. Minus 1 over 3x squared. Yep, 1 over square root 1 minus x squared. Cool. If we just plug in 0 in for x, then we end up getting 1 minus 0 inside the square root, which is just 1. Square rooted is 1. Underneath 1 is 1. 1 minus 1 is 0, divided by 0. So this is, again, going to be 0 over 0. The only other thing that we might want to do, just real quick, is multiply both top and bottom by 1 minus x squared, square root of 1 minus x squared. So this is going to be 1 minus square root 1 minus x squared, which is still 1 minus 1, so whatever. And this is still going to be 3x squared times the square root of 1 minus x squared, which is still going to get us a 1 and a 0 in the denominator and a 0 for the entire numerator. So nothing's changed. It just looks a little bit nicer so that it's not going to be like this compound fraction that we're trying to take a derivative of. Alternatively, it might not be that bad, but I don't really want to do it. Yeah. Might actually be easier the other way around. It is, actually, because there's no product rule. Ugh. Ew. I guess. Okay, so this is still going to be 0 over 0, so it's still indeterminate. So we could still use L'Hopital's rule again. Right, so limit x goes to 0 of. Now this is 1 minus x squared parentheses raised to the negative 1/2. So when we take the derivative of this, d dx, we're going to get a negative 1/2 times 1 minus x squared raised to the negative 3/2 times 2x, negative 2x. So this is going to make a positive, because negative times negative gets us a positive. 2 times 1/2 is going to get us 1, so our constant is gone. So now we just have x over, parentheses, 1 minus x squared raised to the 3/2. The minus 1 ends up going away, over 6x. So, if we divide out x from both the numerator and denominator, then that's gone. And then we can multiply both top and bottom by 1 minus x squared to the 3/2. So in the numerator, we just have 1. And in the denominator, now we have 6 times 1 minus x squared to the 3/2. When x is 0, this is just going to be able to get plugged in. So now we just get 1 raised to the 3/2 is still 1 times 6. So now we get 1/6. I didn't even write the... Didn't even write the options. All right, so A, 0. B, 1/6. That's going to be our answer that we select here. C, 1/3. D, 1/2. And E, 1. So there is a curve whose equation is the following: 2x squared plus 3x minus 2xy minus y equals 6. It has two asymptotes. Find them. So, for asymptotes, right, this is where a function has these approach values. If we're just doing like 1 over x, right, it has these singular values at x equals 0 and at y equals 0. But, like, how do we find those, right? From the original function, 1 over x, we've got a little bit of a problem, right? This is going to be where our function, the limit of f prime of x as x approaches either a or plus or minus infinity, depending on what it is, then this is equal to some slope value that's just a constant. So in the case of our horizontal asymptote, right, the slope value that our function is approaching is going to be 0. All right, so the limit as x approaches plus or minus infinity for f prime at x is going to be 0. And like, that's all well and good, but what about 0, right? F prime at x is undefined. Again, all cool, but what about some other function that ends up with like slant asymptote? So what's going on here, right? This is y equals mx plus b. Our function has a particular m, a particular slope that it's approaching. Cool. How do we find that? So it could be that our first derivative is going to approach a constant value at either, again, infinity or at a particular location. The other option is that the limit at that particular point, x going to a or going to plus or minus infinity, is going to be taken on the second derivative of that function, and we're looking for the zeros or undefined Right. In the case of a vertical asymptote, you can get undefined values. So for this one, we just take the generic derivative of this entire function. We do eventually want to find dy dx, but we can hold off. Right, if you want to do that, obviously, just go for it. Say like, okay, you're taking a derivative with respect to x of this whole thing. And then where do you get just functions of x and y, and where do you get places that have a dy dx? So, derivative, bring down the power. It's going to make 2 times 2 is 4, times x to the first power, times dx. So I'm taking the generic derivative operator. It's going to say, take the derivative of this thing, no respect. Can't get no respect. We're not going to do anything to our x's, or sorry, we're going to just take the derivative of x's and y's. So the derivative of x's becomes dx, the derivative of y's becomes dy. Some people might not like it. Hi, Zach. So 3x just going to become 3 dx. Okay, the next one is going to be a power rule. So we have to use both parts here. It's going to be negative 2 dx times y plus, which because it's a minus out front, it's going to be a minus 2x dy minus dy is equal to 0. Take the things with dy's and move them over. Everything else should have a dx. So, yes. This is going to be 4x plus 3 minus 2y parentheses dx is equal to okay, 2x plus 2y plus 1 parentheses dy. So dy dx is equal to 4. Yeah, right. Keep the y where it is, move the rest of the stuff down. So 4x plus 3 minus 2y over 2x plus 2y plus 1. So here we'd want to look for, 2x plus 2y, not another 2x. Okay, so this is going to be our first derivative. if we want an asymptote, then that means that we'd probably take the limit as Francesco T. Hello. Buenos dias. Hope everything's going well out there. I unfortunately do not speak Spanish beyond that, but Latin mammal with opposed thumbs. Trying to learn math. Nice. Well, if you have any particular subjects or questions or anything like that that you'd like to explore, please let me know, and we'll try to accommodate as much as we can. Right now, I'm working on cracking the GRE, which is the Graduate Record Exam. This goes back to 2002, so it's quite an old book, but we still try and do some fun stuff. I was just about to. Oh, yes. And if you haven't met any of the other people in our group, this is our. Yes. So we're doing Calc 2. This is our streamer group that we've kind of cooperated with. Thank you for the follow. All of these wonderful people spend at least one stream a week doing all of the math stuff. Granted, some people are like, super complex stuff, and some people are like algebra to calculus. So, nice. Where are you in your mathematical journey? Learning machine learning and data science. Nice. I would especially recommend e to the 2i pi, who is Zach, one of our friends over there. He has learned a bit of machine learning, done some, I think he was specifically working in data science, and Penn Center has also been doing some stuff with that as well. I myself took a class in machine learning, or neural networks was the actual name of the class for my master's degree, but that was like basically 15 years ago. So I've been teaching math anywhere from basic algebra all the way through differential equations for the last 15 years. And I say the last 15 years. I've been here for 2. This is Yorkshire, England. Welcome. Once we actually get some sun, like after 8 p.m., I might start leaving the window open and watch the colors sap out of the sky. It's pretty fun. It's also really fun when it's still light outside at 2 in the morning. UK rock music, nice. For now, yeah, we're trying to work on Calc 2 type stuff, but like I said, if you have anything that you're interested in trying to piece together, figure out whatever, I can try and help if it's above that kind of excuse me, if it's above that kind of like differential equations level, can help try and figure some stuff out. We do mathy type streams on Mondays and Wednesdays. Monday is usually like math communication, so I'll go and pull up a paper from archive. We were doing this week one on math history, Galileo and Huygens. This was the connection between Vincenzo and Galilei, and Constantine and Christian Huygens, who were father-son pairs. Uh, this particular researcher was looking at the relationship between the fathers and sons and their relationships to music and mathematics. So what they did to like figure out mathy type stuff from the perspective of music. It's pretty cool. Um, yeah, we ended somewhere around here. So I'm going to pick that up on Monday again, and we'll read through it. That's not what I meant to do. I meant to switch that back. There we go. Well, I'm glad you found it too. And like I said, feel free to follow any of those other people. They're also doing mathy type stuff at least once a week, provided they're in town, you know. Music theory, yep. Yep, definitely. Once you start getting like really weird convolutions or Fourier series or any of that stuff, you start getting into the realm of sound waves and also whatever else you've got going on. So it all just combines together. It's really cool. Fully agree. All right. Claude Shannon, yep. Oh, and on Tuesdays and Fridays lately, we've been doing game streams. Tuesdays have been blueprints, and Fridays have been usually Against the Storm, which is like a super long game that we've been playing for almost 2 years now. No, it's more than 2 years. But I also play Elite Dangerous and space colonization type game now. It wasn't always colonization. And I have like my own system of colonies, many of which are named after famous mathematicians, physicists, and the like, to try and get people to like be interested and be like, who's this person? I've never heard of them, and then go look them up. So I'm a big fan of math history. I tried teaching my students math history when we were doing stuff in class, which, mixed results. Okay, so this thing is causing us some trouble because if we want a specific value, if we want a specific value for our slope, then we're going to end up with like some weird combination of stuff. So that is why we really need to take the second derivative of this. And then set it equal to 0. So we're going to take the derivative of the top, and we get 4 dx. This is going to be gross. Actually, that's just 4 because it's with respect to x on the other side. Yeah, definitely. And they just look at it and think that it's like, bunch of sums and stuff. And it's like, no, there was a mathematician by the name of Harold Jacobs. I don't know if he's still alive. But Harold Jacobs did or wrote a book that I have here called Mathematics, A Human Endeavor. And so this is a kind of, I want to say it's for the algebra-ish age. But yeah, it was published in 1970. Mathematics: A Human Endeavor. I got that one for free off of one of my retiring colleagues. Okay, and then the 3's gone. At the bottom, we've got a 2 plus 2 dy dx. And then the 1's gone. Okay, and then dy dx is each going to be one of those fractions. So this is going to make a compound fraction, which is pretty gross, but it's all right. So that's the other thing, is that the other side is 0. So we can just throw everything off and melt it. Right? Multiply both sides by 2 plus 2 dy dx. And then this is going to go to, again, a 0 over there. So 0 is equal to 4 minus 2 times this 4x minus 2y plus 3 over 2x plus 2y plus 1. Multiply both sides. Still 0. By 2x plus 2y plus 1. This is going to get it out of this particular location, and then also multiply it to the 4. So 0 is equal to 4 times 2x plus 2y plus 1 minus 2 times quantity 4x minus 2y plus 3. This is going to be 2. Right. Divide both of these by 2. Still got a 0 over there. So now we get a 4x plus 4y plus 2 minus 4x plus 2y minus 3 is going to be a 6y. X's go away on this side. Interesting. And then that's going to get a minus 1, so that's equal to 1, so y equals 1/6. And then where it's undefined, I guess, is the other one. All right, ads are going to play here, so I'm going to go for 3 minutes, and we'll be right back. Thank you so much, everybody, for coming. If you don't know me already, my name is Obi-Wan Pez. This is N-Simplex Pachinko, and we'll be back soon. Righto. Welcome back, everybody. So we said that the only other real possibility here is if our second derivative is undefined, it should be a vertical asymptote. So we're going to get a 2 plus 2 times, and then that's going to be the fraction from above. Or no. Yeah. It is equal to 0, because, anyway. All right, multiply out. So we get 2 times the quantity, 2x plus 2y plus 1, plus 2 times the quantity, 4x minus 2y plus 3, is equal to 0. We can get rid of our 2's, because again, that's just going to be 0. And then we get 2x plus 2y plus 1 plus 4x minus 2y plus 3 is equal to 0. Our y's divide out, or subtract out, and that is what we're looking for. 6x plus 4 equals 0, so that's 6x is negative 4, so x is going to be negative 2/3. Nice. So it depends. It kind of depends on what you're going for. So oftentimes, if I'm just looking for like some sort of answer, I'll run through a calculator. I'll try and graph it. I'll do, some sort of data visualization or whatever. If I'm trying to do like data, then obviously I'm going to need to simulate stuff. Like there's no point in doing stuff by hand if you need to do like 1,000 things. But if I just need to like look at the relationships of the numbers that are there, then yeah, I love calculating stuff by hand, even if it's sometimes just absolutely fruitless and like, why did you do this? It's good exercise, quite honestly. Speaking of exercise, while we're talking. Das though we know hoist. So, if anybody has any free weights or anything like that laying around, or just heavy objects. Just give it a good minute. Yeah, no worries. So, there's actually a game that I play, which is called Exponential Idle. We've done a few streams on here where they have some events where it's kind of interesting just to be like, okay, what's going to happen if, what are the connections between the numbers that are here? And so it's just going to be taking all of the equations that we have and then relating them together and saying like, okay, what is going to be kind of an optimal move in any particular case? What is going to maximize the value that I want in any particular case? So it doesn't always work to do stuff by hand, but I prefer it. And like I said, it's a good exercise. Yeah, that's good enough. And then we switch to 1. And up and over. Trying not to crack myself in the head with this. It's happened occasionally. Yeah, you don't want to forget theory. And like I said, this is mostly just to like try and figure out what the relationships are between the quantities that I've been like kicking around for a whole bunch of time. All right, good enough. Good times. Sometimes lifting weights gets everything a bit tighter, so I do recommend like trying to loosen up afterward. Stream is off. How dare. Yeah, no worries. Okay. So we got 2, right? Y is equal to 1/6 and x is equal to negative 2/3. Oh no. That is not what they have here. Curses. Huh. Man, I really screwed that up then. 2x squared plus 3x minus 2xy minus y equals 6. Huh. Okay. Okay, well, that's one way to go. Crap. Well, that didn't work. I don't know exactly what happened here, but if anybody wants to check it out, you could try and figure it out. Huh. I'm going to trust my spouse's notes on this, probably more than my own even. However, this is going to be, this is a y equals, so we can factor y out from both of these and then kick it to the other side, then move 6 over to the other side. So this is going to be y times the quantity on the positive side, 1 plus 2x. Yep. X equals negative a half. Yep. That is, in fact, one of the possible X answers. Cool. Okay, and then we have X times 2x plus 3, which is going to be here. So y is equal to, no, wait, minus 6. Two x squared plus 3x minus 6. So y is equal to 2x squared plus 3x minus 6, all divided by 1 plus 2x. Okay, so here, our asymptotes occur when 1 plus 2x is equal to 0, so that means that x is equal to negative 1/2. And Okay, yeah. And this is going to have a slant asymptote because the numerator has a higher degree than the denominator. This is simple pre-calc stuff. So I don't know what I did down the other side, but you know, that stuff is true. You want it where the limit is going to get you, where the limit is going to get you, the limit of the second derivative is going to get you 0. But it's kind of the problem, right? So there's also a lot of other stuff going on there. Anyway, with this, the slant asymptote we can find by taking 2x squared plus 3x minus 6 and dividing as a polynomial 2x plus 1. This is going to be x, 2x squared plus x is being subtracted to find the remainder, which is 2x. And then minus 6 drop down, so here this is going to be a plus 1. And that's going to be a 2x plus 1 subtracted off from 2x minus 6 is going to be a negative 7. So this is a negative 7 over 2x plus 1. So x plus 1, or y equals x plus 1, is going to be the slant asymptote. Yes. So asymptotes are those lines which the function is approaching, but not actually quite reaching. So here, in this case, this slant asymptote y equals mx plus b is going to represent the linear function that our rational function is approaching as it goes further and further out toward x equals negative infinity or positive infinity. So they go out like that. The typical one that's like y equals 1 over x is a rational function. It's the basic rational function where you have polynomials top and bottom. These polynomials are 1 and x. So, nice and easy. Yep. So our asymptotes here are x equals 0 and y equals 0. Those are the singular values where we're just not going to get an answer. So here, if we multiply y equals 1 over x into a, like, this same form that we had up here for the original equation, it's sort of like conic sections a little bit. Then what we end up getting, again, here, in fact, they are conic sections. They're hyperbola. Yep. We get x times y equals 1. And so like the product of our two values, x and y, is just going to get us 1. So they have to be reciprocals of each other every time. Which means that 0 really throws a wrench in this because you can't have a reciprocal of 0. It doesn't work that way. Anyway. The difference between the actual function and the asymptotes goes to 0, or will tend to 0. Whether they be going toward a specific value, so x equals a, or a specific line, so y equals mx plus b, or a, well, I mean, this is also a specific line, but y equals 0 or y equals 5 or something like that. Midnight math streamers? Your time? I don't know. Penn and Dr. Gold seem to be the ones who are on late for me. But I think Penn's got a lot of other work to do. Gonna do an all-nighter. Yeah. Um, hmm. Yes. Because a friend of mine found this and was like, whoa. It is a Pez dispenser of Obi-Wan from the Clone Wars set that came out in like 2008, something like that. And like, um, Ewan McGregor. I don't look all that much like Ewan McGregor. If you pull up like his photos on stuff, even when he's dressed up as Obi-Wan Kenobi, I don't really look all that much like him. But both of us look identical to that Pez dispenser. Math spell books on? Awesome. Yeah, I'll probably be going for another 15-20 minutes, and then we'll probably need to be ducking out because it's gonna be that's gonna be like 2:30. So self study, yeah. All right. Well, this was the much faster way to go, definitely. Um, to end up turning this all into just a rational function and then saying, "Oh, what do you remember from pre-calc?" Right? Way easier. Trying to do this the calculus method got us really screwed up, and I got completely wrong numbers. Um, so I don't even know what happened exactly. I don't tend to think about it that much in like a huge way. However, really, that's a basic physics course. Let's see. Uh, Differential forms of fundamental equations. That seems useful. No, 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 no worries. No, I got you. I mean, I can't necessarily speak with any authority, right? Because physics is not actually my area of expertise. I have been an armchair physicist for a very long time. I read, eh, you know, I read these. Stephen Hawking's A Brief History of Time and Universe in a Nutshell. And, like, they're very cool. They help me out to understand what exactly is going on with, like, a lot of the physics concepts and stuff like that. But they're not they're not things that I understand on a technical level. But I got you. Hmm. In theory, you could think of it like kind of a way in which the universe is trying to approximate uh, flatness, where it's basically trying to get as flat and even as possible. It's possibly even like, all of the other forces are a bit like springs, where if you have a center of energy, be it fusion energy or what have you, it's creating a lot of pressure outward, and like kind of like a wound up spring, it's trying to get loose. It's trying to get undone. Entropy collapses when there's thermodynamic equilibrium. So like, yeah, if there is 100% uniformity, then like, is there really anything going on there? No matter how big or small the system is, right? When physicists and everybody get together and start saying like, okay, when this reaction, whatever it is done, like nothing's happening. Eventually, all the individual molecules settle down into a standard or average motion, where like you're gonna get essentially complete homogeneity, right? Everything's the same all the way through. It's very boring. And then we just turn our attention to something else and be like, "Ooh, look at this," because there's not even a point. Yeah, if you start going like even further, you know what? There is a good video. Uh, Like, if you want some serious existential crises, if you... nope, don't do that. Don't play somebody else's video. Terrible idea. Yeah, if you want some serious existential crises, watch this to the end. Right, because eventually, so this is a video by a guy who goes by the handle Melody Sheep, and it takes excerpts from people's talks and things like that, and physics shows and Nova specials on PBS and things like that. And then it extrapolates into the future, like, okay, we're going to increase the amount of time that passes every 5 seconds. I think it doubles every 5 seconds. And also the, like, music increases tempo every 5 seconds or something like that. I could be wrong. And then it eventually gets out to what's going to happen in 100 trillion years, and it's like, this is absolutely unbelievable. It's completely nuts. What's going to happen? What do you mean? What's going to happen in 100 trillion years? Like, the we have no concept of what's going to happen in 10,000 times the current length of the universe. But, like, the universe will still exist in some form or another, in theory. So when it gets that far out, like, entropy starts winning because, like, a new stage in development essentially happens. And it just keeps going. Time keeps moving on. It just keeps going on forever and ever and ever. I mean, not forever, but just about forever. Okay. Let's see if we can't do one more. So number 6. And I mean, this is the end of the page. Oh, sucker. Okay. Hmm. That Y. Where'd that 2Y come from? Oh my goodness. So that's probably my problem. Man. There was no 2Y here. Yep, completely. It's just 2x plus 1, which is what we had over there. Right, so 2x plus 1 is equal to 0, so x equals negative 1/2. Bingo. Alright, let's get rid of this stuff, because now this is all wrong. Hang on. See, perfectly salvageable when you actually know what you're doing. Curses. I think I also forgot to do half the problem here for the other one that I was doing, so that could have also been a problem. Okay. So we're going to take the derivative with respect to x of the top, which gets us 4 minus 2 dy dx. Yes, I did, because I just did the L'Hopital's rule, essentially. Ugh, so terrible. Okay, divided by 2x plus 1. You cannot take the derivative of both. Minus, going to be the original 4x minus 2y plus 3, divided by 2x plus 1 parentheses squared. And we multiply by the derivative of the bottom, which is going to be 2. This is probably going to look a lot better. It's also going to be a little gross, but it's fine. All right, if we multiply by 2x plus 1 squared, then we end up with 0 still. 4 minus 2, parentheses, 4x minus 2y plus 3, all over 2x plus 1, all multiplied by an extra 2x plus 1, because we're going to multiply everything through all the way with 2x plus 1 parentheses squared. And then that's going to get us over here. 2 times 4x minus 2y plus 3. Zero equals. We can get rid of the 2 that's here with the 2 that's here and the 4 that's here to a 2, which now makes a 2 parentheses 2x plus 1 minus that 2x minus 1 and the 1 in the bottom go away. So now this is just 4x minus 2y plus 3 inside parentheses. Minus 4x plus 2y minus 3. Zero equals 4x plus 2 minus 4x plus 2y minus 3 minus 4x plus 2y minus 3. Those are the same thing. Well then. I mean, I shouldn't be surprised. Zero equals. So that's going to be a negative 6 plus 2 is going to be a negative 4. X's, we get minus 8 plus 4, so minus 4x. And y's, we get plus 4y. Interesting, yeah. That's gonna just get rid of our 4's and get everything away from the y. So these are both going to go that way and be multiplied by a quarter and become positive on the other side. So y equals x plus 1. Awesome. That's it. So we did get it. It just, I had to do it right. Also, doing it by calculus is going to take longer than remembering your properties. Because again, here, this is the sum total of work that we had to do in order to find those same things without calculus. So, which would you rather, right? You probably want to do the one that's going to be the easier in the quicker amount of time. So in this particular case, just finding the properties of rational functions for this particular function works great, right? It is something you can solve for y and just get it. So that's pretty nice. Yeah. All right. I think we'll probably call it there and go visit one of our educational streamers. So we're going to go over to Window. Interesting. Yeah. Okay. Events. Interesting. Filter by category. Okay. Ah. Hey Zach, that caught me off guard. Mostly because I don't have my music on right now, and it's still very loud. Good times. um, hmm. Currently, we're trying to find somebody to raid. However, yep, caught me right at the end. We did the first 5 problems out of the Chapter 2 review for cracking the GRE. So we made it through most of finding the limits of stuff. All right, let's go see Moo. Moo Hoodles is a science communicator streamer here on Twitch and has really awesome astrobiology background and talks astrophysics all the time. I really love astrophysics. Astrophysics was my first love, as I showed you my collection of Stephen Hawking books. Most of which are probably out of date slightly, but it's fine. I'll figure it out eventually. I want to thank everybody for coming. I will be back on Friday for some probably Against the Storm. We are currently working on Elite Dangerous because there is an expedition going on. We are currently at Beagle Point, which is basically like on the opposite end of the galaxy from where we are, i.e. Earth. It's absolutely amazing and beautiful and wonderful. The creators of this game have done a wonderful job. So if you ever get the chance, playing keyboard and mouse is okay. Playing HOTAS with the stick and throttle, also really nice. Uh, Allegedly, if you're gonna like get good at it, keyboard and mouse is actually the way to go. Alrighty. Anyway, I'll see you all later. Thank you